Slide a book across a table, it scrapes, slows, and stops, and nothing you do to the table will hand that motion back. The perfect trade between kinetic and potential energy is broken. This video tracks the missing energy and finds that the book still balances. No joule is ever lost. Until now, every internal force we allowed was conservative. The work such a force does between 2 points never depends on the route taken, which is exactly what lets a potential energy function store that work and give it back. Friction refuses the rule, drag the book straight across the table, and friction removes some kinetic energy. Drag it to the same endpoint along a wandering detour, and friction removes more. The force opposes the motion at every step, so a longer path means more work taken away. Same start, same finish, different work. Whenever the work done by a force in moving an object from an initial point to a final point depends on the path taken, we call that force non-conservative. No potential energy function can be defined for such a force because the stored value would depend on how you arrived. Now take a closed system whose internal forces are both conservative and non-conservative and follow it from an initial state to a final state. The total work done by the internal forces splits into two pieces, the conservative work plus the non-conservative work. The conservative piece is path independent, the non-conservative piece is path dependent, and the conservative piece is the part potential energy already tracks. The change in potential energy is defined as minus the conservative work. Substituting turns the total work into minus delta U plus the non-conservative work. The work energy theorem gives a second handle on the same quantity. The total work equals the change in kinetic energy. Set the two expressions equal, and the delta K equals minus delta U plus the non-conservative work. Move delta U to the left side, and the result is clean. The non-conservative work equals delta K plus delta U. But delta K plus delta U is exactly the definition of the change in mechanical energy. So the non-conservative work equals the change in mechanical energy. With only conservative forces, the left side was zero. That was conservation of mechanical energy. With one path-dependent force at work, the right side comes alive. Mechanical energy is no longer constant. Read the result with friction in mind. Friction opposes the sliding at every instant, so its work is negative. Negative non-conservative work makes the change in mechanical energy negative 2. The book's kinetic energy drains away, and no potential energy rises to catch it. But mechanical energy was never the whole ledger. The system's other column, non-recoverable energy, gains exactly minus the non-conservative work, a positive deposit whenever friction acts. So the total change in the system's energy is the change in mechanical energy minus the non-conservative work. And since the non-conservative work equals the change in mechanical energy, the difference is exactly zero. Total energy is conserved without exception. What has happened is a transfer, not a loss. The missing mechanical energy has become non-recoverable energy. Energy the system can no longer organize back into the motion of the book. The non-conservative work measures precisely how much made the one-way trip. Processes that generate non-recoverable energy are called irreversible processes. Irreversible is a strong word, and running the movies backwards shows what it means. Reverse the film of a ball rising and falling under gravity, and the playback looks perfectly normal. Every frame still obeys the physics. Reverse the film of the sliding book, and you watch a book gather warmth out of the table and launch itself across the surface. The energy totals would still balance, yet it never happens. Disordered thermal motion does not spontaneously reassemble itself into organized motion. That one-way character is the mark of every process with non-recoverable energy. The conservative world runs equally well in both directions. Friction gives time an arrow. One restriction remains, the system has been sealed, now let energy cross the boundary. Whatever the system gains, the surroundings lose. the change in the system's energy equals minus the change in the energy of the surroundings. The exchange runs through two named channels. The first is external work. The surroundings push or pull on the system, producing coherent organized motion. Its sign convention, external work is positive when the surroundings do work on the system, and the surroundings energy falls. It is negative when the system does work on the surroundings, and the surroundings energy rises. The second channel opens when the system sits in thermal contact with the surroundings, so thermal energy can flow across the boundary. Call the flow Q with the same orientation. Q is positive when energy flows into the system, negative when energy flows out. What this channel changes is not coherent motion, but the random thermal motion of the molecules inside, raising it or lowering it. Add the two channels and the balance reads external work plus Q equals the change in the system's energy. That equation is the first law of thermodynamics. Other forms of energy can enter as well, radiative energy, for example, but work and heat are the two flows the first law names. Step back and read the whole ledger. Conservation of mechanical energy was one column, kinetic plus potential, constant only, while every internal force is conservative. Non-conservative forces move energy out of that column into non-recoverable form. External work and the heat carry energy across the system's boundary. Through all of it, total energy balances exactly. Two questions remain. First, whether every conservative force can be identified and assigned its potential energy. Second, how to account for a non-conservative force like friction, which acts right at the boundary between the object and the surface. The next step follows friction down to that surface to see where the missing energy actually goes. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.